In this video, we'll solve few interesting problems from signals and systems. Actually, you will find a series of videos where we'll be discussing the problems from signals and systems. I hope it will be useful to all of you. This is the part 1. Let us start. The first problem that we will consider here is this one. Consider one signal xt and it is given as this one, 2 sine 10 phi t plus 5 15 phi t plus 7 sine 42 pi t plus 4 cos 45 pi t. And this signal is passed through an LTI system having an impulse response, this one, h of t. And h of t is given as 2 times sine of 10 phi t upon phi t times cos 40 phi t. Now we need to find out the output of the system. So choices are given. So we need to find out the output of this LTI system. Now this problem is very interesting. Now to tackle this problem, we'll use this following approach. So let us consider the system h of t. This is an LTI system. Now when we'll apply one input signal x of t, then output yt is nothing but convolution between this xt and h of t, right? Now here the signal is given, this one. It's a combination of few sinusoidal signals. Here 4 sinusoidal signals are given or combined with certain weightage. Now we can find out the frequency of this xt because each sinusoidal signal will have a single frequency. So as it is having 4 such sinusoidal signals, so x of t should have 4 discrete frequencies, right? So these frequencies, so if I consider x of t as a cos omega naught t, then a is called amplitude and omega naught is your angular frequency, that is in radian per second. So if I compare this signal, we can see that this is one signal, one part, 2 sine 10 pi t. Thus, this signal is having one frequency 10 pi radian per second. Second component is having 15 pi t, so its frequency is 15 pi. Similarly, this signal is 42 pi, is having 42 pi frequency, and last one is having 45 pi radian per second. So these 4 discrete frequencies are there in the signal x of t. Now this kind of signal is passing through a system, an LTI system. Now if I consider this system as a filter, because any system can be considered as a filter, some frequency it can allow to pass and other frequencies will be rejected. So x of t, if it is sinusoidal, a cos omega naught t, and if it is passing through a system, then output is again sinusoidal. So if input is sinusoidal to an LTI system, then output yt will be again sinusoidal with same frequency. Its frequency is omega naught. Again we will get omega naught, and again if it is cos, it will remain cos, but amplitude is modified. So here a times m of omega naught, magnitude of some function of omega naught, that is actually the absolute, this one, magnitude of h of j omega. Okay, so h of j omega is the Fourier transform of h of t, right? So its magnitude part is m of omega naught at frequency omega naught, and phase is also added with this omega naught t, and this phase at omega naught for this h of j omega that we can compute. Then we will get the output signal yt. So you can notice here that this output signal, the amplitude is modified by this factor m omega naught. If m omega naught is large, close to 1, then we can say that the output signal is present, means signal can pass through the system and it is available at the output end. But if m of omega naught, this factor is very small, close to 0, then yt is almost 0. The meaning is that the xt signal cannot pass through the system. So that signal is not available at the output end. So it is one kind of filtering. So depending on the filters, we can get the available output at this end, right? Now, this x of t, a cos omega naught t, if I take Fourier transform, it will contain two impulses because cos omega naught t is having single frequency omega naught. So that two frequencies are at omega equal to omega naught. Thus it is del omega minus omega naught, this term. Another frequency at omega equals to minus omega naught. That is the function is del of omega plus omega naught. Okay. So this Fourier transform I have discussed in detail in one of my recent video. So you can go through that video. I'll be giving the link for this video in the description. Now, if I consider h of j omega like this, okay, this is an ideal one, but in practice you may get different shape for h of j omega, right? But for discussion purpose, I have considered one h of j omega, one such h of j omega pattern like this. So if the figure is like this, it implies that beyond omega c, the h of j omega is 0, gain is 0, and 0 to omega c, its gain is flat. Means all frequency within 0 to omega c, it can pass through. But if frequency is more than omega c, it will be attenuated to 0. That I can show in this way, that if this signal, this omega naught, is within this omega c, so these are the spectral for input signal. If input signal is within the pass band of the system, then signal will be available at the output end, right? Then output is simply a cos omega naught is same. Input and output is same. However, if this x of omega naught is having these two impulses at omega naught and minus omega naught, which are beyond this pass band, outside this pass band, then output will be 0 because this signal cannot pass through the system. This is within the stop band, right? So this is the main philosophy of the filters. We want to use this concept to solve this problem. It's really interesting problem. We need to understand in a better way. Okay, so here main task is first to find out this h of j omega for this ht. Once we can find out this h of j omega, then we can understand that these frequencies 10 pi, 15 pi, 42 pi, 45 pi, these are within the first band or not. If it is within the first band, that signal will be available at the output end. If it is not within the first band, it is not available at the output end. Okay, so let us find out h of j omega. So h of t is given as 2 times sine 10 pi t upon pi t times cos 40 pi t. Its Fourier transform will be h of j omega that we need to find out. Now to solve this, We'll consider a small section, this part first. Sine 10 pi t upon pi t. So that I'll call it a function g of t, a signal g of t. G of t equals to sine omega c t upon pi t, this form. So in this case, omega c is 10 pi. So if this is one signal or one function g of t, right, its spectral, its Fourier transform will be like this, that it is flat up to omega c, and left side also minus up to omega c, magnitude will be 1, and beyond that it is 0. Because this signal is a sinc function, and the spectral of sinc function is a gate window or window function. And how to remember this thing? You see, if I don't consider this phi t, if it is only sine omega ct, then this sine omega ct signal will contain two frequencies. One is at omega c, other one is minus omega c. Okay, but whenever I'll multiply by 1 upon phi t with this sine omega ct, then the spectral is continuous from 0 to omega c, and it is flat. 1 means all frequencies are present up to omega c, not only at omega c. So only sine omega ct is having discrete fractal at omega c, but whenever we will multiply 1 upon pi t, it will become a sinc function, and Fourier transform of sinc function is a gate window, and the cutoff frequency will be this frequency, sinusoidal frequency omega c. That is important, and gain will be 1, right? Now, as it is multiplied by 2 times cos 40 pi t, and this form, so if it is gt, 2 times gt cos omega naught t, its Fourier transform we can compute using modulation property. So whenever signal is multiplied by one carrier signal like cos omega naught t, then its spectral is shifted around omega naught. Generally, this kind of method is used to get modulation in communication. Okay, modulation means to translate the spectral from low frequency to higher frequency around omega naught. Okay, so if I consider this property 2 gt cos omega naught t, its Fourier transform will become these two. One is shifted to right side, g of omega minus omega c. Other one is g of omega plus omega c. And you can note here, sometimes I write j, sometimes we will discard j. So j is only for notation. In h of j omega, j is only just for notation. Basically, it is a function of omega. So we'll assume that this h of j omega could be complex. Thus, we have included j. Okay, but actually, it is just function of omega. So sometimes we'll discard this j. So don't be confused. So this gt, its factorial is suppose g of omega or g of j omega. So whenever it is multiplied with 2 cos omega naught t, then one spectral will get around omega naught. Same spectral, g of omega minus omega naught, it's a shifted right side by omega naught, and this one is shifted left side by omega naught. Okay. So in our case here, this is your gt, and here omega c is 10 pi, and this gt is multiplied by 2 times cos omega naught t. Here omega naught is your 40 pi. So this omega c is 10 pi, omega naught is 40 pi. Now we want to draw the spectral of h of j omega. This is our task. So we'll start with g of j omega. So this is your g of j omega. You can see this omega c is 10 pi. So up to 10 pi, it is flat. Both sides, 0 to plus 10 pi, 0 to minus 10 pi, both sides is flat, 1. And beyond that, it is 0. So this blue curve is for g of j omega, means Fourier transform of this function. Now whenever there is a modulation, means multiplied by 2 cos omega naught t, this spectral will be shifted right side as well as it is shifted to left side, and it will be around omega naught. So omega naught is 45. So it will be shifted around here, this 45. Okay, you see. So this g of j omega is now shifted here. We'll get g of omega minus omega naught. Omega naught in this case 45, and we'll also get g of omega plus omega naught. This is the window around minus 45. Okay, so this green one is actual h of j omega. So this is for g of j omega. So we can remove this one because this is not within this h of j omega. So I remove that part. Okay, this is the spectrals, true spectrals. Its magnitude is 1. Okay, this is your pass band, and beyond this one, this side stop band, this also stop band. Similarly, this is the pass band, this is your stop band, this is also stop band. Right? Now we will see the frequency content in the XT signal. The first one, if I consider 2 sine 10 pi t, this signal is having a frequency 10 pi. So 10 pi here, we'll have one impulse here, one impulse here, as is sine wave. So this I'll consider downward, and this I'll consider upward. So this thing I have discussed in detail in my previous videos. So one important thing, if it is sine or cos, we'll get only impulse at certain locations at omega naught only. Omega, okay. Here in this case is 10 pi t. So frequency at 10 pi only, 10 pi and minus 10 pi. And you can clearly see that these two frequencies, they're outside this first band. So it will be rejected by the filters. So at the output, it should not be available. Okay. Next, 5 cos 15 pi t. So another frequency is at 15 pi here. This is 1 and minus 15 pi. Again, these two frequencies, they are outside this band, pass band. Again, it will be rejected. Next one, this 42 pi t, 7 sine 42 pi t. So it is here, this 42. It is within 40 to 50. Okay. Similarly here. So this signal is within the pass band. Okay. So this signal can pass through. It will be available at the output end. The last one, this 4 cos 45t is also within 40 to 50 within the first band. Similarly, this side also first band. So it can also pass through. So these last two, this 42 pi t and 45 pi t, these two signal can pass through the system, and it will be available at the output end. Thus, output yt will be only these two, 7 sine 42 pi t plus 4 cos 45t. Right? Thus, the answer C is correct. I hope this is clear to all of you. This is very interesting problem. Try to understand it clearly. If you have any doubt, you can make comment in my video at the below. I'll try to explain it. Right? Now we'll move to the next problem. Right? This is your next problem. One transfer function of a real system h of s is given as this form: h of s equals to a times s plus b upon s square plus cs plus d. Look at carefully. This is your h of s. One numerator, one denominator functions are given, and there a, b, c, d, these are positive constants, it is mentioned. Now it is asked that The question is that this system cannot operate as, means we cannot make the system, this system, to as any of this: low pass filter, high pass filter, band pass filter, or integrator. So which one we cannot design using this function h of s? That is the question. Okay, can we design low pass filter with this form? By we can choose any value for a, b, c, d, any positive value, positive constant, including 0. Remember, I can put a, b, c, d, any of this 0. Okay, but not negative, right? 0 or positive. But can I make low pass filter out of this, or high pass filter, band pass filter, or integrator? Right? So you need to understand this one. So to solve this problem, first we will try to get the poles and zeros of the system for this, at least for this few: low pass, high pass, band pass, and integrator. Then we will try to compare it. Right? Now for low pass filter, now it shows that h of s is second order system. Denominator, the polynomial is second order, a square term, quadratic, a square into cs plus d. Thus, it will have two poles. Okay, so poles are nothing but the solution of this denominator equals to 0. So I will have two solutions. So I'll have two poles. And we can have 1, 0 from this function. It function shows that we can have two poles and we can have 1, 0. Right? Now, for low pass filter, the requirement is that for second order system, we should have only two poles. There should not be any zeros. Right? So this is, I have discussed this thing in one of my lectures, that the pattern of low pass filters. Okay, you will see that if the system is having only poles, no zeros, system will behave as low pass filter always. Okay, so as frequency omega is increasing, its magnitude will go on decreasing. Thus, it will behave as a low pass filters. Right. Now for high pass filter, band pass filter, and integrator. For the high pass filter, along with these two poles, we should have two zeros at origin. Okay, if we are having two zeros at origin, then only system will behave as in high pass filters. Okay, so number of poles on left hand side should be same as number of zeros at the origin. That is the requirement for high pass filter, because at very high frequency this numerator denominator should cancel out and it should give a constant value. So for that we should have two zeros at the origin. Okay, for two pole system. For second order high pass filter, two poles on left hand side and two zeros at the origin. Okay, now next, for band pass filter, two poles on left hand side and 1 0 should be at origin, particle to 1 0. So you see the differences. If it's second order, obviously you should have two poles, fine. But if there is no 0, it is behaving as a low pass filter. If it is 1 0, it is behaving as a band pass filter. If there is two zeros at the origin, then it will behave as high pass filter. Right? And integrator, this one, if I apply xt, at the output I will get integrated of form of this signal xt, integration of x tau d tau from minus infinity t, if h of s is of this form 1 upon s. Because if it is so, then its impulse response will be ut, and if I consider ut, if I take convolution of ut and x of t, that is nothing but integration of this thing. That thing also I have discussed in detail in one of my videos. Please go through all those things. So this is one integrator. H of s should be 1 upon s. It's the first order. Okay, one pole at the origin. That is the only integrator. Okay, now how can I make this one, this H of s? Right? Whether we can make low pass filter, band pass filter, high pass filter, or integrator. Let us check. So from that, easily we can make on low pass filter, because so this is not actually b equal to 0. This b should be equals to 1 and a equal to 0. Okay, so this b equals to 1, remember this one correction. So this b equals to 1 and a equal to 0 will give you a constant numerator 1 and denominator 2 poles, right? So b should be equals to 1 here and a equal to 0, or b can be constant also. Okay, not necessarily 1, it could be constant as well. So it will behave as low pass filter, because numerator there is no zeros, a equal to 0, thus no zeros, only 2 poles, we can make low pass filter. And if we consider b equal to 0, then it will be as upon a square plus cs plus d, means 1 0 at origin you will get. Thus the system will behave as band pass filter. But for a high pass filter we need 2 zeros, a square term in numerator, that is not given here. The square term is absent, so I can't make 2 zeros at the origin, no way. Okay, so obviously we can't design high pass filter of this form, right? And integrator, so answer is given that D is also a choice. We cannot make integrator, but I think we can make integrator. How? Because if I consider C, D, these two are zeros, so denominator will be a square, and numerator, if I consider B equal to 0, it is absent, it will be A into S, and A equal to 1. So A1, B0, C0, D0. It will become S upon A square. So it's pole zero cancellation. Using pole zero cancellation, we can simplify that, it is 1 upon S. So integrator we can design if I consider B equal to 0, C equal to 0, D equal to 0, and with A equals to 1. It can behave as integrator as well. So integrator can also design, but that is a choice. But high pass filter, of course, we can't design. No way we can design, because 2 zeros at the origin is not possible with this form. Okay. So officially these two answers are given. This is the problem from GATE E 2022, right? But from my concept, this D can be designed. D means integrator can be designed as well. So only thing, high pass filter cannot be designed, right? Okay, so we'll go to the next problem. The next problem is this one. Two discrete time linear time invariant systems with impulse response h1n and h2n, they are connected in cascade, and here delta n is given as Kronecker, obviously Kronecker delta, means delta n equals to 1 when n equal to 0, otherwise it is 0. Now we need to find out impulse response of this cascaded system, overall system. So h1 is given, it is del n minus 1 plus del of n plus 1, h2n is del of n plus del n minus 1. So we need to find out overall impulse response of this cascaded system. Okay, so these are 4 choices. We need to solve it. I hope the problem is clear to all of you. Now we can try to solve it. So to solve this problem, we'll start with this one, that this is a signal xn. One first system is h1n, then again it is followed by second system H2n, then we will get ultimate output Yn. So these two systems H1n and H2n, they are cascaded one after another. Now this overall impulse response H of n is given by the convolution between these two. That is very simple because the output at this end will be convolution between xn and h1n, and output yn is actually the convolution between output at this end and h2n. So if I replace this one, you will see that this output yn is nothing but xn convolution h1n convolution h2n, and output yn we can write as xn times one system hn its convolution. Okay, thus these two convolution will give you the overall impulse response. So h of n is basically h1n convolution h2n, right? So we need to compute the convolution of these two sequences. That's all. It's a very simple problem. Now h1 is given as del n minus 1 plus del n minus n plus 1. h2n is del n plus del n minus 1. So how to compute this convolution? So I'll give you, so this convolution we need to find out, and I'll give you three methods. The first method is very simple one. Just I'll consider this is a sequence. As this is finite sequence, I can write as this way: del n minus 1 plus del n plus 1, convolution with del n plus del n minus 1. Now I'll expand it. So its convolution is a linear operator. Okay, so this is convolved with del n. Again, this will be convolved with this one. Then we'll take addition like this. So this one is now will take convolution with first term del n. This is again taken convolution with second term del n minus 1. Then we'll add these two. Now again we can consider this thing. It's linear operator. So convolution between this and this and this and this. Then plus. Okay. Now convolution between this and this. So what we can consider? So this I can consider as a system. Okay, and you know that xn convolution del n is always xn, because if impulse response is del n, if input is del n, output is also del n, meaning is that if I apply xn, output is also xn. From that concept, xn convolution del n is nothing but again xn, because this system is not doing anything. So whatever signal at the input side, you will get same as output side, because the impulse response is same as del n, right? But if impulse response is del n minus 1, so you have applied input del n, output you are getting del n minus 1, so one delay, so it's a delay system. So whenever we will take convolution, we will get delayed output. So xn convolution del n minus 1 will give you x of n minus 1. Similarly, if it is n minus 2, it will be x of n minus 2, like that. Okay, so this we can use it very simply. Xn convolution del n is xn. Xn convolution del n minus 1 will be x of n minus 1, delayed one. So if it is delayed by k amount, k samples, so input signal is also delayed by k sample at the output end. Okay, so this del n is now convolution with del n minus 1. So you will get same del n minus 1 because you are taking convolution in del n. So this input will be output, same thing. Now this is convolution with del n minus 1, so it is shifted, okay, delayed by 1 unit. So del n minus 1 will become del n minus 2, del n plus 1 will become del n, because one delay. Earlier it was n minus 1 minus 1, it will become n minus 2. This is n plus 1 minus 1, it will become del n only, one delay. So this is the output, very simple. So you see, we can rewrite these things: del n minus 2 first, then del n minus 1 plus del n plus 1. So this is answer is C, is correct. You can take second approach. So first we can consider the sequence H1n, and you can notice that it is del n minus 1 and del n plus 1. So del n is absent. So at origin it is absent, it is 0. And del n minus 1 is right side. This is your del n minus 1. This is your del n plus 1 is this one before 0, before the origin. Okay. Similarly, this one, this h2n, del n is present. So at origin it is value is 1. And delay component next one is also 1. Okay. So these are two sequence we need to take convolution. We can use tabular method. In this axis, this side, I can plot h1n, and this vertically I can plot h2n, these two. So h1n 1 0 1, and here 1 1. Then I'll multiply these elements by this number. Okay, so 1 into 1 is 1, 1 into 0 is 0, 1 into 1 is 1. Okay, so you'll get same thing. Similarly for this one, you'll get same one. So 1 0 1 1 0 1. Then you will consider this one diagonal line you will consider, and within this diagonal line all elements you need to add up. Okay, so this is, and this is the origin h1n, this is the origin, and h2n, the first one, this is the first row is the origin. So first row second column, so this element is the within the origin. So whenever we will collect this one, this 2 0 plus 1, that will be at origin. Okay, and before that this will be the 1, and after this one 0 plus 1 is 1, and then it is only 1. So that I have shown here. So first I have considered this one 0 plus 1, that is 1, that I have written here at the origin. So this arrow will give you that indication that it is at origin. Okay, then this one is 1 because only one element, I can put it here 1. Then this one I can consider after that. So it's right side. So 0 plus 1 is again 1. And this one, last one here. Only 4 elements will be there. Rest all other elements are zeros. We will not consider. So this one, you see, we can easily write as this is your del n, this is your del n plus 1, this is del n minus 1, this is del n minus 2. Okay. Same answer we have obtained. The third method is that we can use Z transform. So h1n I can convert to h1z. Similarly h2n I can consider h2z. So h1z will be, so this is 0 is fine. So this element should be multiplied by z minus 1. So 1 into z minus 1. This element should be multiplied by z. So 1 into z. So this is your h1z. h2z is 1 plus 1 into z minus 1. So I have discussed Z transform in detail in my lectures. Please go through these lectures if you have some doubt. Okay, so we can find h1z and h2z, and then we can use this property. Hn is convolution between these two. Then h of z will be product of h1z and h2z. So first h1z is z plus z inverse. The second one is h2 is 1 plus z inverse. So these two I can multiply. I can expand it. So we'll get this one. If after expanding 1 into this one is same thing, 1 plus z inverse. Then if I multiply z inverse with this one, so first one will be z into z inverse is 1, and z inverse into z inverse, z to the power minus 2. Okay. Now we'll take inverse z transform. So h of n will be, so this one, this constant will the origin. At origin it is 1. And z to the power minus 1 is the next one, 1. Z to the power minus 2 will be next one. And z on the left hand side, and its element coefficient is 1, thus it is 1. So if it is present with certain coefficient, that coefficient we will consider here, and it is absent, we'll place 1 0 there. Okay, so in this case, this is the sequence, and this sequence is nothing but equals to this sequence. Okay, so we'll get again the same result. I hope you have understood this problem. Next problem is this one. So consider this problem. One continuous time domain signal xt is given. It is defined as xt equals to 0 when mod t is more than 1, and x of t equals to 1 minus mod of t when mod of t is less than 1. Now, Fourier transform of x of t is defined as this one. X of omega is minus integration of minus infinity to plus infinity x of t e to the power minus j omega t dt. That is the standard definition of Fourier transform. Now, maximum magnitude of x of omega we need to find out. Okay, so actually we should understand the spectral of x of omega, and then we need to find out x of omega naught, omega, the maximum magnitude. So where first we need to identify where the maximum will be there, and then we'll try to find out its magnitude. So the shape we can draw. So as it is given that t mod t more than 1, it is 0, this side is 0, this side is 0, but within plus 1 and minus 1, it is 1 minus mod t. That means that its maximum value is at 0, and right side is decreasing to 0. It will decrease to 0 at t equal to 1. Similarly here, it will become 0 at minus 1, but it is straight line here. So this xt is basically a triangular signal. And we know that for triangular signal, its spectral is sin square. Okay, and sin square, its maximum value is at 0, omega equal to 0. So xt, its Fourier transform is x of omega, and we know that at 0 it is the maximum value. So x of 0 we need to compute, and x of 0 is nothing but area under the signal xt. That is one property. Okay, I have discussed this thing, all the properties, 14 properties in detail in one video. Okay, in the previous video. Please go to that video. It will be useful. So area under xt signal will be equals to capital X of 0, and capital X of 0 is the maximum value of x of omega, because its pattern is sin square. I'm not drawing the sin square function, but just we will try to compute at 0 what is the maximum value. So at 0 the maximum value is the area under this signal. So we need to just find out the area of this signal. So this width is 2, height is 1. So area of this triangle is half into base into height, half into 2 into 1. Okay, so if you simplify, you will get 1. So its maximum magnitude will be 1. Very simple. And this is the last problem we'll consider. This problem says that the causal realization of a system transfer function h of s having poles at 2, minus 1 and minus 2, 1, and zeros at 2, 1, minus 2, minus 1. Then this is, we need to identify whether the system is stable or unstable. It's a real or complex. It's a all pass filter, low pass filter, or high pass filters. Okay, so which one is correct? We need to understand this model. So for that, first we will try to find out, or try to plot or place the poles and zeros on S plane. Okay, I'll consider on S plane. This is a real axis, this is the imaginary axis. So this 2, minus 1 means real part is 2 and imaginary part is minus 1. So there we will have one pole, and another pole is minus 2, 1. So I'll show this thing. So this is 2, minus 1. Here I have one pole. Here minus 2, 1, I have another pole. Similarly, I have two zeros. So these are two zeros, 2, 1, 2, 1, 1, 0, and minus 2, minus 1, there is 1, 0. So this is the pole zero locations for this system. Now we need to identify whether this is stable, unstable, real or complex, or what type of filter it is. Okay. So you can see that poles are these two locations, 2 minus j and minus 2 plus j. Zeros are 2 plus j, 2 plus j, and minus 2 minus j. Now poles are not in conjugate form, okay, because these two are not conjugate. Rather, they are opposite to each other, sign change only. I can take minus sign common with 2 minus j again. So one pole is here, one pole is here. They are not in conjugate. If it is conjugate, it should be real parts should be same, and imaginary parts is just one is positive, other one is negative. But this is not the case. So these two poles, they are not in conjugate form. Similarly, two zeros are also not in conjugate form. Thus, numerator and denominator both are complex. As a result, h of x is complex. So hs will be real if all the poles and zeros are either real or in conjugate pair. Okay, if I have two poles, then those two poles should be in conjugate pair. The two zeros, both the zeros should be in conjugate form. Then only hs will be real polynomial. So this is not the case. Thus hs is complex. Second one, you see we have one pole on right hand side of S plane, this pole. So because of this pole, as it is on right hand side of S plane, the system is unstable. Okay, so if all the poles are on left hand side of S plane, then only it is stable, otherwise unstable. So this figure shows that one pole on right hand side, thus the system is unstable. Next one, whether it's low pass, high pass, band pass, all those things. Now you see poles and zeros, these pairs, this pole corresponding zero, they're equidistant. From here, its position is distance is 1, this is also 1. Similarly, this zero and pole, they're equidistant. So this pair both are equal distance, thus it will behave as all pass filter. Okay. So our answer is H of S is complex, unstable, and all pass filter. These three: complex, unstable, all pass filter. So this one, unstable, complex, and all pass filter. Okay. So we'll continue more problems in next video. And if you enjoyed this one, you may press like button. And if you want to get more such videos and you have not subscribed this channel yet, then you may subscribe it, because I'll be uploading lots of videos in this channel. I hope all of those videos will be useful to you. So thanks for watching. We'll discuss more problems in next video. Thank you.